Hello and welcome to this lecture. So in this lecture, we'll delve deeper into the span. We saw that span was a very important idea. We need to understand span very well if we are going to make progress towards solving linear equations and all that. So first begin with the easy case, right? In all of math we've developed like that, right? We consider a small possibility and then use logic to extend it to larger and larger cases and then slowly build up into a complete theory, okay? So we'll look at span of one vector. This is very easy. Now, if u is the vector that I am considering, a1 to an, if u is 0, it's very trivial, okay. So, if u is 0, the span of 0 is 0 itself, so you only get the origin. So, it's a very easy case, we won't consider that. So, we'll look at u being non-zero. If u is non-zero, what is span of u? The span of u? The answer is actually quite easy, is a set of all Cu, where C belongs to the scalar field f, which is basically Ca1 ... Can, right. So, all possible C, you scale this, that will be your span of u. Now, what is this? This we have defined generally as the straight line passing through the origin in u. Okay, so why is this inspired? This is inspired by the case when n is 2. When n is 2, we have seen that if you have a point, u which is not 0, and then if you look at the span of that, that is nothing but the straight line passing through the origin in u. So, even in 3 dimensions, you can make a diagram like this. Okay, so now 3 dimension you can't show in 2 dimensions easily, but we usually make this sort of diagram where we imagine that these two axes, x and y axis, are on the plane of the slide. Okay, they are on the slide, okay, that you're seeing, and the third axis is coming out of the slide out. Okay, so this is a visualization you can do for 3-dimensional spaces, and here also if u is somewhere here, then this is a straight line, passing through the origin. So you can think of these in n and 2 and 3, sort of visualize in 2 and 3 quite easily. But if you go to n greater than or equal to 4, visualization is really limited. You have to sort of fall back to this 2 case or 3 case and then sort of visualize the axis. It's really not possible. It becomes very confusing. So visualization here is very difficult, and that's what makes sometimes linear algebra a little bit more complicated than it should be. Okay, so when you can't visualize, you get a little confused about how to think of vectors. So usually what people do is they fall back to the n equals 2, n equals 3 case. The n equals 2 case we saw extensively, right? We saw it in great detail. So n equal to 3 we didn't see in great detail, we're seeing it in general. So what I'll generally do in these larger n cases is to give you illustrations with n equals 3 and sort of appeal to your intuition to visualize the more general case. Okay, so span of one vector is very easy. It's line through the origin and u. Even in larger dimensions, we think of this set as the line through the origin and u. Okay, set of all Cu. All right, span of one vector, easy. Okay, what do we do for span of two vectors? Right, so we go step by step. Okay, from 1 to 2 we proceed. So span of two vectors, particularly with respect to, see, what is the problem we are trying to solve? We are trying to solve membership, right? So given your vector u, so if you go back to the one vector case, given a vector u, and if I give you a vector w, can you determine whether w belongs to span of u? Okay, that's the kind of question I'm asking. So for one vector is very easy, right? The span of u is simply all multiples. So given w and u, you can easily determine whether w is a scalar multiple of u. So simply take each coordinate, divide by the coordinate of u, right? You should get the same answer, isn't it? So, but if both are 0, that's okay. But if both are non-zero, then you have to divide and you should get the same answer for all the ratio of the coordinates, right? So, it's a very easy condition to check. So, doing span membership for one vector is very easy. Okay, now if you do two vectors, what do, right? So, if you have two vectors u and v, and supposing I were to ask if w, another vector, belongs to the span of these two, I really need to understand the span very well, right? So, let's look at the span very closely and ask what is the span of uv when u is one n-dimensional vector and v is another n-dimensional vector. We'll assume u and v are both not 0, right? If you assume like both are 0 or one of them is 0, you fall back to the previous case, right? So, it's a very trivial case. So, we'll consider the case where both u and v are not 0, okay? So, here we have to really use our logic and our sense of how to solve these kind of problems. So, here is the first question that I'm going to do. So, here is the first idea. Okay, the first idea is will this reduce to something that looks like a one dimension? Okay, so that's the idea. And here is a question that you ask. Let's say there is a constant c, a scalar c, such that v is c, u is cv or v is cu. Okay, let's say that's the condition. This is a simplifying condition. You will see that under this condition, if u is a multiple of v or if v is a multiple of u, right, scalar multiple of u, this case what happens is any linear combination of u and v ends up being either a linear combination or either a scaling of v or a scaling of u. Okay, so if u is cv, right, you can put u equals cv. then C1u plus C2v is simply C1c plus C2 times v, okay, some scaling of v. On the other hand, if v itself is a scaling of u, then C1u plus C2v is actually a scaling of u. Okay, so this case is actually a very simple case. You don't really have two vectors, it reduces just to one vector. Okay, so in this case, span of uv becomes either span of u or span of v. Okay, so you don't have to really consider uv. So it falls back to the previous case. It's almost as if one of these cases is 0, right? So that's what is the case here. So this case is given the name of linearly dependent. If you have this condition true, then you say that u and v are linearly dependent in the sense that the span of two vectors actually reduces to just the span of one. Okay, so these two are linearly dependent vectors. Okay, so if one is a multiple of the other. On the other hand, if you can establish that there is no constant c, no scalar c for which u is cv or v is cu, if these guys are not multiples of each other, then you have the case that you cannot reduce the span of two vectors to span of one. Okay, so this is not possible. So when you can't do this, then you say that u and v are linearly independent. They are not linear multiples of each other, so they are linearly independent. So the real question is, how do you establish this independence? Okay, so if you have any hope of solving the span membership problem, right, if I give you a w and if you want to find u and v, whether the combination of u and v will give you w, you should be able to determine whether u and v are linearly dependent or independent. If you can't, then you can't really solve the problem. If they are linearly dependent, the problem is maybe very easy, you know, it's a span of just one vector and you can do the membership easily. If they are linearly independent, on the other hand, the situation may become slightly more complicated to determine span membership. Okay, so how to establish this independence is an important question. So let's see how to do that next. Okay, so it turns out there is a process, a very simple and elegant process called elimination, which will help us determine linear independence or dependence. Okay, so here again we'll assume u, v are both not 0 and u is this vector, v is this vector. I'm going to further assume a1 is not 0. Okay, so we'll come back and relax this assumption later. For now we assume a1 is not 0. When a1 is not 0, I'm going to do this very clever trick of replacing v, or instead of considering this new vector w. Okay, what is this new vector w? It's v minus, notice what I've done here, a1 is not 0, so I can divide by a1. I've taken this u, I've divided by a1. Okay, after dividing u by a1, okay, I will have a 1 here, no? If I divide by a1, I'll have a 1 here. I'll multiply by b1. Okay, so I have b1 by a1 into u, that will give me b1 in the first coordinate. And then what will I do? I'll do v minus that guy. Okay, so when I do that, my first coordinate of w is going to end up being 0. Do you see that? It's very easy to see what I've done here. So u remains the same. Okay, I'll keep u as it is. Instead of v, I'll consider this new w, which has got this 0 here, and then it's got a whole bunch of other terms, b2 minus b1 by a1 a2, so on till bn minus b1 by a1 an. Right? Do you see that? This is the clever idea of elimination. So elimination eliminates one of these values in v to make it 0. That's the idea in that. It eliminates this coordinate from consideration. Okay. Now, what is the big deal in elimination? What have I done in elimination? Notice elimination is nothing but a linear combination of v and u, right? W is actually a linear combination of v and u. And this v has a coefficient of 1 and this has a coefficient of something which is b1 by a1. Okay. So it turns out, interestingly, even after elimination, the span remains the same. Okay, the original span that you had uv is the same as the span of uw. Okay, so this is slightly non-trivial sort of fact, a very simple fact. Nevertheless, this is the crux of the argument here. Okay, so even after elimination, you have not lost the span. Span of uv is the same as span of uw. Okay, so why is this true? Here's a quick proof. You can see very easily that a linear combination of uv can be written as a linear combination of uw. So every linear combination of uv also belongs to span of uw. Okay, so it's very easy, right? So you see here, what have I done here? I have v here. Now v can be replaced as w plus b1 by a1 u. So you replace that, you get a linear combination of uw. So every linear combination of uv is actually a linear combination of u and w. And other way around is also true. Any linear combination of u and w is also a linear combination of u and v. Why? I can replace w with v minus b1 by a1 into u. Very simple, right? Very simple arguments. So this is always true in math, right? Every single argument is very simple, but when they are strung together, you get a really complicated result at the end. Okay, at least non-trivial result at the end. Okay. So by these two arguments, you see that span of UV and span of UW are the same. Every linear combination of UV is a linear combination of UW. Every linear combination of UW is a linear combination of UV. So the span remains the same. Okay. So now comes the question of what happens to this W. When you do this, W could be all 0 or W could be non-zero. So it turns out if W is all 0, okay, if W becomes the 0 vector, then V becomes equal to B1 by A1 into U, right? If so, in that case, U and V are linearly dependent. Okay, we have established by elimination that U and V are linearly dependent very, very easily. On the other hand, if W is non-zero, then it turns out there is no C such that U can be CW or W can be CV, right? So that's very easy to establish. Why? Because see, W is non-zero. So one of these guys is non-zero. The first guy is 0. So how do I make W as some constant into U, right? It can never be done, right? So here is 0. Okay. So unless so the only constant you can have is 0 itself. Now if 0 itself has to be there, then W has to be 0, and that is not true, right? So clearly, because of this A1 being non-zero and W having the first coordinate 0, these two cannot be linear scaled versions of each other. That's the critical argument. So this A1 is not 0 and this W is 0. So these two cannot be scaled versions of each other. So that rules out the case of linear dependent and become linearly independent. So because of this elimination, we are able to determine linear dependence and independence very easily between two vectors. Okay. So now this can be used further for span membership. I have not yet talked about it. We'll come to it soon enough. Okay. Now there are other cases. We didn't consider all the cases. For instance, UV both could be 0, which is very trivial, or U could be 0, in which case span of UV becomes this. V could be 0, in which span of UV becomes span of U. So it rolls back to the previous case. However, if U is non-zero, but A1 is 0, what do you do? I was assuming A1 is not 0, right? What do you do? In that case, here is what you do. It's very easy. Since U is not 0, there has to be some I such that AI is not 0, right? There has to be maybe A2 is 0 or A3 is non-zero, right? A2 is non-zero or A3 is non-zero. Something has to be non-zero here. Otherwise, you may not be non-zero. So what you do in that case is you exchange A1 and AI. You modify the U and V. Okay, both U and V you have to modify. Okay, you have to modify both U and V. I have not put that very clearly here. Okay, so we know that there has to be some I such that AI is not equal to 0. So what do I do then? I start by exchanging A1 AI and B1 BI. Okay, so that's what I do. Once I find the AI such that AI is not 0, I will exchange A1 AI and B1 BI. Okay, I modify my U and V by this exchange, and then I will eliminate with that. Okay, so A1 is not 0 now, right? Because I've exchanged it. So my first vector is not 0. I will eliminate. After I eliminate, I will exchange back again. Now what will happen in the ith coordinate? AI will not be 0, but the W, for the W corresponding to the ith coordinate, will be 0. So from there you can determine whether the modified versions are linearly independent or not. Okay, this you can proceed. So this is the main idea behind elimination, and so you can get some practice with this elimination with just the two vector case of longer length. We'll do that a little bit later, but this is the crux of the idea. This elimination to determine quickly whether there is linear dependence or not is a very, very important idea. I hope you get it, and we will use this and exploit this extensively as we go forward to longer and longer cases. Okay, so here is the generalization and proper definition of linear dependence and independence. I was giving this definition of there is a C such that U is CV or V is CU. Turns out it's not a very clean definition. Here is a very clean definition of linear dependence and independence. Vectors UV are said to be linearly dependent if there exists C1 C2 such that C1U plus C2V is 0, with at least one of C1 and C2 being non-zero. Basically, a non-trivial linear combination of UV should result in 0. Okay, in that case, we say that the vectors are linearly dependent. Okay, so this covers the previous case. You can see this is exactly equivalent to U being CV or V being CU. Think about why that is true. One of these is non-zero. I can keep it on this side, move the other to that side and divide by that guy, and I will get this one. Okay, either this or that. So these two are equivalent, but this is a very nice way to write it. Okay, vectors UV are said to be linearly independent if a linear combination of UV being 0 implies C1 is C2 is 0. So the only way to get 0 as a linear combination of UV is the trivial way to get it, which is basically 0 times U plus 0 times V. That will always give you 0, and that is a trivial way to get it, and there is no other linear combination that gives you 0. So that is linearly independent. Okay, so here is a notation alert you have to be very, very careful about. So here I've put 0 here. What is this 0? This is actually a vector 0, right? And here I put a 0. What is this 0? This is a scalar 0, okay? So, it's very painful to distinguish between the vector 0 and the scalar 0. In most cases, from the equation, it's very clear. On the left hand side, you have a vector, right? If I write a vector equal to 0, clearly I mean that this 0 is a vector 0. On the other hand, here I have a scalar. If I put C2 equals 0, clearly I mean a scalar 0. No point in, distinguishing. Some people write a bold 0 and all that, or you can put an underline below. It's all painful notation, but I guess 0 is so trivially easy. So, I'm not going to distinguish between the scalar 0 and the vector 0. I hope you can think about it and distinguish it, okay. So, linear dependence or independence of two vectors clearly can be very easily established by eliminating, making one non-zero and their corresponding thing 0. Check if that is possible. If that is possible and the 0 guy is non-zero actually elsewhere, then they are linearly independent. If this is fully 0, then they are linearly dependent. That's the idea here, okay. So, here is example. I'll urge you to really practice this very carefully. You can do this very easily, right? So, you have here, this is A1 not 0, this is 0. So, you do this minus this into 2. You will get the answer very easily. Here you will get a linearly dependent case. This minus this into 2 will end up in 0 here. This is a trivially linearly dependent case, and this also, you can quickly see this is very easy to determine. You don't have to do elimination or not. This has got a 0 here and it's got a 1 here. Okay, that's the idea, right? If you have any coordinate with 0 and 1, then clearly they have to be linearly independent. They cannot be linearly dependent. They have to be non-zero, of course. Both are non-zero. Then that would be the case. Okay, so it's easy to establish. Make sure you understand how this works out in detail. Okay, thank you very much.